non-zero, if this is non-zero, these guys will have no net shift until the k plus 2 will have a 0, which means a DC net shift. And the net shift actually is qk plus 2 at 1 time 1 is a to the kb over 4 pi k factorial. So you can adjust the a and b to get whatever you like. Here is an example that didn't look like a chain system, but we can turn it into a chain system. Yeah, we have time to discuss this example. Any question about this? Look at it, it looks like very confined, right? I mean, it's just all the things are forced by U1 and just they have you to play around here. So it doesn't seem like it covers the wide class systems, but it actually does. So here's an example. And we give this example in 241, I guess. So, and you were required to watch this lecture for the non-holonomic system, so you should have seen it before. So I have a rigid body, say in the spacecraft or something, and we have a robotic arm here. So you have this guy, and it extends. I can extend the length. So I have like L, this is in the plane, okay? So I can change L with time. And I have one rotational degree of freedom for the body, so theta of the body, have no control over, no direct control over. And I have a direct control over the robotic arm. So this is the angle of the robotic arm epsilon, okay? Because there are no applied torques, we have conservation of angular momentum. So you can show that. This is what we had actually in the lecture. We derived kinetic energy or Lagrangian, and we show that theta is an ignorable coordinate. So conservation of angular momentum partial L partial theta is 0, so gives you partial L partial theta dot is constant, which is theta dot plus some function of L. Please go and redo it. This is constant, and yeah, it's constant. So if you start from rest, this constant will be 0, right? Because this constant is the initial value of theta dot plus this function times epsilon dot at the initial. If we start from rest, this is 0 from rest. So this equation is a Pfaffian form, first order in velocity. So it's like a non-holonomic constraint. So it defines a kinematic system. It defines a non-holonomic system or driftless system, whatever you want to call it. We have 3 generalized velocities. We have epsilon dot, we have theta dot, or let's say L dot. And we have theta dot, right? Only two of them are free because of this constraint-like equation. So let's say the 2 are free like we did in the lecture where epsilon dot and L dot, okay? So I can write them as epsilon dot is 1 here and 0 there, L dot is the other way around, and theta dot from this equation, I can fill the last, which is negative f of L and 0. So this is the corresponding driftless system or kinematic system. This is G1 and G2. Obviously, it's not on a chain form, right? Because I have this function that is not linear. The chain form are all linear in coordinates and controls. This is not linear in the coordinate. So I'll do the following trick. I'll do the following approximation. I have f of L, right? So I will expand this around some equilibrium. So this is f prime of L naught plus, sorry, delta L, plus some higher order terms. And actually I have f of L here multiplying by epsilon dot, so I'll have epsilon dot here, epsilon dot there. And I will do the following. I will define my Q1 to be epsilon, that's fine. Q2 to be the change in the length. And Q3 to be the following. So I'll take theta plus this constant term, multiplying psi, so that when I differentiate, this constant term goes away and I end up only with the linear term plus some higher order terms. And I'll even divide by the coefficient to have the coefficient 0. So if you differentiate, now I get q1 dot is psi dot, which is u1, and q2 dot, which is delta L dot, which is simply L dot, which is u2, q3 dot, from here is theta dot plus this guy times psi dot. So from the equation, you will have only the linear term, which is, where is the linear term? So we have this guy multiplying psi dot, here is this guy multiplying psi dot, and we have negative. I divide by the negative f prime, we have just delta L multiplying psi dot. Delta L is actually q2, and psi dot is u1. But instead I have higher order terms, that's fine, yeah, we'll worry about it later. But if you can see here, this is a chain system, right? I will justify the negligence of the higher order terms in a minute, but do you agree that this U thing is a chain system? U1, U2, the previous U times U1, right? Okay. So I can easily do my motion planning. Q1 and Q2 are directly. Q3 is just coming from the lead bracket between Q1 and Q2. So if you want to steer Q3, that's easy. U1 is A sine, right? And U2 is what? What's U2 to steer for Q3? Come on, guys. What is U2? Yeah, this is the first order lead bracket, the easiest thing. What is U2 to steer?
Just B cosine omega t.
Yeah, B cosine omega t. Very good. Okay. So, okay, we did the steering for the approximate system. Let's see, does this higher order term, will it affect things or not? Okay. I will call this thing, this whole thing. Q2 is what? Q2 is delta L, right? So this is the linear term in L. The higher order term is the nonlinear term in L. I was expanding a function of L, f of L here. So this is a nonlinear function for each of L. Actually, there is also multiplying U1 here. So everything is multiplying U1. So this is a some nonlinear function of L multiplying U1. Okay. So I apply this control system, which will exactly steer my chain system, which is approximation of the original system. So in reality, I'm applying this guy to the full system. So let's see what happens when you apply this guy to the full system. Okay? Let's get the Q3 exact. So Q3 at 1, say, exact. This is Q3 initial, yeah, that's fine, plus the integral of whatever you have here, right? So this is actually h of L times U1, right? H of L times U1. So this is h of L times U1. H of L of t dt. So let's get L of t, please. Can you get me L of t? Yeah, I have U2 here, which is L dot. I just integrated to get L of t. Integrate this guy, you get B over omega sine omega t, correct? Okay? So now you have a signal that is sinusoidal at some frequency, and you have a nonlinear function of this signal. Can you give me an expression for this signal in time? Again, I have a sine wave. That's okay. I have a sine wave here, okay, at some frequency, and I have a nonlinear function of this sine wave. What is the output? Can you give me a form for it? What is the Fourier transform will give to you? Well, this will be some amplitude at the fundamental frequency, some other amplitude in general at twice the frequency. If it's an odd function, I can expand it in a sine series, or sine and cosine with some phase shift, plus yada, right? So there will be also harmonics, but there might, because of non-linearity, there can be higher harmonics. If it's pure linear, then it's this guy, right, or some amplitude. And the FFT is exactly giving you these amplitudes. If you do FFT for this signal, you pass the sine to whatever nonlinear function and get the output, do the FFT. The FFT will give you what? Peaks with this length at this frequency, another peak at this frequency, and so and so, right? This represents the linear term, the quadratic term, and so and so. So I don't care about these things now, but I'm sure that it's on this form, right? So I'll go and substitute it here to get Q3 exact. So this is Q3 of 0 plus integral of H1, which is the linear term that I included already, okay? H2 sine 2 omega t plus yada yada times U1, and U1 was what? U1 was A sine omega t. So this is A sine omega t, dt. This should be over the period. So what do you think? Sine omega, sine 2 omega. What's the average of that? 0. Sine omega, sine 3 omega. 4 omega, all zeros, except the linear term that we already picked. So this is already what we have from the theory, right? Coming from chain system. Okay? Yes, please.
So for H small to expand it in the Fourier series and have constant coefficients at the main frequency and multiples, this means that this function is periodic.
No.
H.
Well, yeah, because the input was periodic. Yes, you're right.
Yeah, but H alone, is H alone periodic? H small h alone is.
This is h of L, and I'm feeding v over omega sine omega t. So the output is multiple at multiple frequencies. You see what I'm saying?
Oh.
This is h of L of t. Okay, so yeah, I'm doing design on the approximate system, but it's actually exact because all the higher harmonics will not affect for this stealing using sinusoid. So in the homework, I'm asking you to do it for our usual example. We have the x, y, and theta. So actually, we have here v and omega, and we know that x dot is v cosine theta, v sine theta, and theta dot is omega. This is our example, right? We started with in the very first lecture. So this is something like cosine, sine, and 0 in v, which is u1, 0, 0, 1 in omega, which is u2. Obviously, it's not in chain system, chain form plus cosine and sine, but you can approximate, right? So the cosine around the origin, this will be just 1, this will be just theta, and with a flip of the order, I would have something like that, x dot and theta dot first, then y dot. So this is u1 now, is approximately u1, this is exactly u2, and this is approximately theta times u1. This is a chain form, right? u1, u2, and then this is the previous state times u1, and so on. Any question? We're done. I thought I would not have time to cover, but luckily we did it. Any question? I will post the homework. The homework is today, but it's actually not about this thing. It's about the controllability. We missed that. So, yeah, it will be due next Monday about the controllability in Lie brackets. Do you have any questions, please? Okay, see you next time.